Right now, billions of miles away, Voyager 1 is sending back numbers that shouldn't exist. Out there, in a place so far from Earth that sunlight takes more than 22 hours to arrive, a small spacecraft built in the 1970s is still alive, still listening, still whispering back across the dark, and what it's telling us doesn't match the calm, empty void we expected to find. Before we drift further into the void together, please take a moment to like this video and subscribe to Cosmic Drift. It helps our sleepy community grow, one star at a time. The idea of the edge of the solar system sounds simple. You imagine a line, a clean border. You cross it, and suddenly you're somewhere else. But that's not what Voyager found. Instead of a sharp line, it found something more like a fog. A slow change. A long goodbye between the sun's warmth and the cold breath of the galaxy. What Voyager is sending back from this strange region is rewriting what we thought we knew. And in the quiet hum of its signal, there's a message much bigger than just numbers on a screen. Let's go back to the beginning. In 1977, NASA launched two spacecraft within weeks of each other, Voyager 1 and Voyager 2. They were built for a simple job: fly past Jupiter and Saturn, take pictures, send them home, then drift into silence. No one expected them to survive this long. The missions were designed to last 5 years, maybe a little more, just enough time to capture the outer planets and send back a few hundred photos. That was it. After that, the spacecraft would run out of power, lose contact, and fade into history. But something strange happened. They didn't die. Year after year, decade after decade, the Voyagers kept going. Their instruments stayed alive. Their antennas stayed pointed at Earth. Their power sources, fueled by the slow decay of plutonium, kept producing just enough electricity to send whispers back across the solar system. And as they traveled farther, they started seeing things no one had ever seen before. Jupiter's great red spot up close, the lava volcanoes of Io, the icy cracks of Europa, Saturn's rings in such detail they looked like frozen music, the storms of Uranus, the blue haze of Neptune, and on one of Neptune's moons, Triton, geysers shooting nitrogen ice into space. These were some of the most beautiful and surprising images ever taken. And they came from two small machines built with technology older than most smartphones today. But the pictures were just the beginning. Once the planetary tour was over, the Voyagers kept flying. There was no reason to stop them, no wall to bump into, no traffic light to tell them to wait. They simply kept moving, carried by the momentum of their original launch, slowly drifting toward the edge of everything we know. And that's when the real mission began. Scientists started calling it the Voyager interstellar mission. The goal was no longer to photograph planets. The goal was to explore the boundary between our sun's influence and the rest of the galaxy, to feel the moment when the solar wind runs out of breath, to cross into a place where the rules are different. This boundary has a name: the heliopause. Think of the sun as a giant furnace sitting at the center of our neighborhood. Every second, it blows out a stream of charged particles, protons and electrons, rushing outward in all directions at hundreds of miles per second. This stream is called the solar wind. The solar wind fills a huge bubble around the sun. This bubble stretches past all the planets, past the asteroids, past the icy chunks of rock at the far edges of our solar system. Inside this bubble, the sun is in charge. Its magnetic field shapes everything. Its wind pushes everything. Its presence is felt in every corner. But the solar wind doesn't go on forever. At some point, far from the sun, the wind gets tired. it runs into something else. A pressure from outside. A flow of material coming from the rest of the galaxy. Interstellar gas, cosmic rays, particles that have been drifting through the Milky Way for millions of years. Where the solar wind finally stops, that's the heliopause. It's the edge of the sun's kingdom. Beyond it lies interstellar space. For a long time, no one knew exactly where this boundary was. Scientists could guess. They could build models. They could run simulations on computers. But they had no way to actually go there and measure it. Then Voyager 1 started getting close. By the early 2000s, the spacecraft was farther from the sun than any human object had ever traveled. It was passing through a region called the heliosphere, a kind of in-between zone where the solar wind starts to slow down and pile up against the incoming pressure from outside. Scientists watched the data carefully. They looked for signs that the boundary was near, changes in the magnetic field, shifts in particle counts, drops in the temperature of the solar wind. And then, on August 25th, 2012, something changed. The numbers flipped. Voyager 1 had crossed the heliopause. It was now in interstellar space, the first human-made object ever to leave the sun's protective bubble and drift into the great unknown. Let that sink in for a moment. A machine built by human hands, launched before most of us were born, had crossed a line that separates our home from the rest of the galaxy. It was no longer inside the solar system in the strictest sense. It was out there, in the cold, in the silence, in the void between stars. And it was still talking to us. The crossing didn't happen the way many people expected. Scientists thought there would be a dramatic change in the magnetic field, a sudden shift in direction, a clear signal that said, "You have arrived." But the magnetic field didn't change direction the way models predicted. Instead, what changed was the particles. Inside the heliosphere, the number of high-energy cosmic rays coming from the galaxy is low. The solar wind blocks most of them. But when Voyager 1 crossed the boundary, the cosmic ray count jumped sharply. At the same time, the lower energy particles from the sun almost disappeared. That was the signal. That was the moment. Not a change in field direction, but a sudden flip in particle population. The spacecraft had stepped from one environment into another, like walking from a warm room into a snowstorm and feeling the temperature drop the instant you cross the threshold. But here's where things get interesting. The interstellar space Voyager 1 entered wasn't what anyone expected. For years, scientists imagined that the region outside the heliosphere would be calm. Quiet, a peaceful void with a thin scattering of particles drifting slowly through emptiness. The word interstellar sounds cold and still. It sounds like silence. But Voyager 1 found something different. The space out there is not calm. It's not empty. And it's definitely not quiet. From the moment the spacecraft crossed the heliopause, it started detecting things that didn't fit the simple picture. Waves, pulses, fluctuations, sudden shifts in density, unexpected sounds. In 2013, just a few months after crossing the boundary, Voyager 1's plasma wave system picked up a strange signal, a kind of whistle, a high-pitched tone rising through the data. Scientists traced the sound to plasma oscillations, vibrations in the thin gas between the stars. The whistles were caused by eruptions from the sun, pressure waves traveling outward and crashing into the interstellar medium like ripples in a pond. But these events were rare. They only happened once a year or so. Between them, the data went quiet. Then, in 2017, something new appeared. A hum. Not a whistle, not a sudden spike, but a steady, persistent tone. A faint drone coming from the emptiness around the spacecraft. Scientists studying the data realized what they were hearing. It was the sound of interstellar space itself. The gentle vibration of plasma. The quiet hum of gas particles floating in the void. One researcher described it like rain. Not a thunderstorm, not a downpour, but a soft, steady rain falling on a window. A gentle background noise that never stops. This hum gave scientists something they had never had before. A continuous measurement of the density of space. Before the hum, they could only measure density when a solar event triggered a whistle. Those events were rare and unpredictable, but the hum was constant. It kept going month after month, year after year. It let scientists track how thick or thin the space around Voyager was as it drifted farther from home. And what they found was surprising. The density of interstellar space was higher than expected. When Voyager 1 first crossed the heliopause, it measured a plasma density of about 0.055 electrons per cubic centimeter. That was already higher than what models predicted for the space outside the heliosphere. But then, as the spacecraft traveled farther, the density kept rising. By 2015, it had increased by about 40 times. Not a small change, a dramatic jump, and the numbers stayed high. This puzzled scientists. They expected the density to be low out there. The interstellar medium is supposed to be almost empty. A few atoms per cubic centimeter at most. So why was Voyager seeing so much more than expected? Several theories have been proposed. One idea is that the material just outside the heliosphere is being compressed. The interstellar wind, the flow of gas from nearby stars, slams into the edge of the sun's bubble. This collision piles up particles near the boundary, creating a kind of traffic jam in space. Another idea involves the magnetic field. As the interstellar field drapes over the heliopause, it may pull electrons along with it, concentrating them in a thin layer near the edge. Both ideas might be partially correct. The truth is probably some combination of effects that scientists are still working to understand. What's clear is that the boundary between the heliosphere and interstellar space is not a clean line. It's messy. It's dynamic. It responds to what the sun does and to what the galaxy throws at it. And Voyager 1 is the only machine we have out there measuring it in real time. Think about that for a moment. This spacecraft, built nearly 50 years ago, is still sending back data that rewrites our understanding of the cosmos. It's not using fancy new instruments or advanced technology. It's using equipment designed before the invention of the personal computer. And, yet, it's giving us the only direct window into a region of space no one has ever explored. That's what makes this mission so remarkable. Not just the distance, not just the age, but the fact that it keeps surprising us. Every year, scientists find something new in the Voyager data. Some unexpected signal, some measurement that doesn't match predictions, some clue about the structure of the universe that we couldn't have guessed from here on Earth. The hum is just one example. There are others. In 2020, both Voyager 1 and Voyager 2 reported another strange finding, a sudden increase in plasma density that appeared out of nowhere. Scientists hadn't predicted it. Models didn't explain it. It just showed up in the data. Some researchers think it might be a pressure wave from the sun, still catching up to the spacecraft, even at this enormous distance. Others think it might be a structure in the interstellar medium itself, a region of denser gas that Voyager happened to pass through. The truth is, no one knows for sure, and that's what makes this so exciting. We're not just confirming what we already believed. We're discovering things we never imagined. Let's take a step back and think about what interstellar space actually means. When you hear the words interstellar space, you might picture total emptiness. A black void with nothing in it. Just darkness stretching forever in all directions. But that's not quite right. Interstellar space is not empty. It's filled with stuff. Very thin stuff, but stuff nonetheless. There's gas. Mostly hydrogen and helium, the two lightest elements. These atoms float through the galaxy in enormous clouds, sometimes clumping together, sometimes spreading out across light years. There's dust, tiny particles of carbon, silicon, iron, and other elements. These specks are so small you could fit millions of them on the head of a pin. But over vast distances, they add up. They scatter light. They block the view of distant stars. There's radiation, cosmic rays, high-energy particles that have been accelerated by supernova explosions, black holes, and other violent events. These particles zip through the galaxy at nearly the speed of light, carrying enormous amounts of energy. And there are magnetic fields, invisible lines of force threading through space, shaped by the motions of charged particles and the rotation of the galaxy itself. All of this material together is called the interstellar medium. And Voyager 1 is floating through it right now. The spacecraft can't see this material the way we see objects on Earth. The gas is too thin to photograph. The dust is too small to detect with a camera. But Voyager has instruments that can feel these things. Sensors that measure the electric and magnetic fields around the spacecraft. Detectors that count cosmic rays. Antennas that listen for vibrations in the plasma. Using these tools, Voyager 1 has been mapping the local interstellar medium for over a decade. And what it's found is a place much more interesting than anyone expected. The region Voyager is traveling through right now is called the Very Local Interstellar Medium. This is the space immediately surrounding our solar system, stretching for a few tens of light years in every direction. This region is part of a larger structure called the local bubble. The local bubble is a cavity in the interstellar medium, a region of unusually low density carved out by ancient supernova explosions millions of years ago. When massive stars died nearby, their explosions blew away the surrounding gas, leaving behind a hollow zone. Our solar system sits inside this bubble, and so does the space that Voyager 1 is now exploring. Within the local bubble, there's another smaller structure called the local interstellar cloud. This is a wisp of slightly denser gas, about 30 light-years across, flowing through our neighborhood from the direction of the constellation Scorpius. Voyager 1 may be passing through the edge of this cloud right now. Some scientists think that's why the plasma density has been higher than expected. The spacecraft might be sampling material from a denser pocket of gas as it moves through this patchy region. But there's still a lot of uncertainty. The structure of the interstellar medium near the Sun is complex and not fully mapped. Voyager is giving us clues, but it's only one data point in a vast ocean of space. Think of it like trying to understand the weather across an entire ocean by measuring the temperature at a single buoy. You can learn a lot from that buoy, but you can't see the whole picture. Still, every measurement helps. Every number Voyager sends back adds to the map, and over time, a clearer picture is starting to emerge. We're learning that the boundary of the heliosphere is not a smooth sphere. It's lumpy. It bends and flexes depending on what the Sun is doing and what pressure is coming from outside. We're learning that the interstellar medium is not uniform. It has patches of dense gas and patches of thin gas. It has currents and flows and regions of turbulence. We're learning that cosmic rays from the galaxy flood into the heliosphere in ways we didn't fully understand before. The sun offers some protection, but not complete protection. And outside the bubble, the radiation levels are much higher. All of this matters. It matters for understanding how stars interact with their surroundings. It matters for understanding how cosmic rays affect planets and moons. And it matters for any future missions that might one day venture beyond the heliosphere and into the galaxy. Voyager 1 is the pioneer. It's blazing a trail that no one else has traveled. And even though it's old, even though its power is fading, even though its instruments are fewer than they once were, it's still doing science that no other spacecraft can do. Because there is no other spacecraft out there. Voyager 2 is also in interstellar space. It crossed the heliopause in November of 2018, about 6 years after its twin. But it took a different path and entered in a different location. The two spacecraft are now tens of billions of miles apart, drifting in different directions, measuring different regions of the interstellar medium. Together, they give scientists 2 data points instead of 1. That's still not much compared to the vastness of space, but it's more than we've ever had before. And the fact that both spacecraft made it this far is itself remarkable. Think about what they've survived. Decades of cold, radiation bombardment, the slow decay of their plutonium power sources, mechanical wear, electronic aging, software, glitches that had to be fixed by engineers sending commands across billions of miles of space. In 2023, Voyager 1 stopped sending readable data. Its flight data system had developed a problem, probably from a corrupted memory chip or a particle strike. For months, the signal it sent back was gibberish. Engineers couldn't understand what the spacecraft was trying to say. It looked like the mission might be over. But the team at NASA didn't give up. They spent months diagnosing the problem from more than 15 billion miles away. They figured out that a portion of the spacecraft's memory had failed, and they found a way to work around it. They moved the affected code to a different part of memory. They rewrote the software. They sent command after command, waiting more than 40 hours between each transmission for the round-trip light time. And it worked. In April of 2024, Voyager 1 started sending engineering data again. A few weeks later, science data came back too. The spacecraft was alive, wounded, but alive. That moment was a reminder of how fragile these missions are, and how determined the people behind them are to keep them going. The engineers who work on Voyager today were not around when the spacecraft launched. Some of them weren't even born yet. They've inherited a machine that was built in a different era, with different technology, by people they never met, and they've dedicated their careers to keeping it alive. That dedication has given us something priceless, a window into a part of the universe that no one else has ever seen. And every day that Voyager keeps transmitting, that window stays open. Let's talk about what the future holds. Voyager 1 is powered by a device called a radioisotope thermoelectric generator. This generator uses the heat from decaying plutonium to produce electricity. It doesn't burn fuel. It doesn't rely on sunlight. It simply takes advantage of the slow, steady release of energy from radioactive decay. When the spacecraft launched, its generators produced about 170 watts of power. That's less than what it takes to run a ceiling fan. But in space, where there's no air resistance and no gravity to fight against, that's enough to keep a small machine alive. Over time, the plutonium decays. And as it decays, it produces less heat, less electricity, Every year, Voyager loses about 4 watts of power. Today, the generators produce less than half of what they did at launch. That's not enough to run all the instruments. So over the years, NASA has had to make hard choices. They've turned off cameras. They've shut down heaters. They've disabled systems that are no longer essential. What's left is a stripped-down spacecraft, a skeleton crew of instruments still collecting data, a few sensors still measuring particles and fields, enough power to keep the radio transmitter alive and pointed at Earth. For now, that's enough. But the clock is ticking. Scientists estimate that Voyager 1 will have enough power to operate at least one instrument until around 2025 or 2026. After that, the power will drop below what's needed to maintain any scientific function. At some point, probably within the next decade, the spacecraft will fall silent. The transmitter will stop. The signal will fade. And Voyager will drift on alone into the endless dark. But silence doesn't mean the end. Even after the radio goes quiet, the spacecraft itself will keep moving. There's nothing out there to stop it. No friction, no drag. Just empty space stretching for light years in every direction. Voyager 1 is traveling at about 17 kilometers per second. That's roughly 38,000 miles per hour. It sounds fast, but compared to the distances between stars, it's barely a crawl. At this speed, it will take Voyager about 300 years just to reach the inner edge of the Oort cloud. The Oort cloud is a vast shell of icy objects surrounding the solar system. It stretches from about 2,000 astronomical units to as far as 200,000 astronomical units from the Sun. Passing through the Oort cloud will take tens of thousands of years, and even after that, the spacecraft won't be close to any other star. In about 40,000 years, Voyager 1 will pass within 1.7 light-years of a faint star in the constellation Ursa Minor. The star is called AC plus 793888. It's a small, dim star that most people have never heard of. That will be the closest Voyager comes to another star system for a very, very long time. After that, it will keep drifting through the galaxy, around the Milky Way, for millions of years, perhaps billions. The spacecraft is so small and the galaxy is so vast that the chances of Voyager ever encountering anything significant are vanishingly low. It will simply float, silently, endlessly, a tiny piece of Earth moving through the cosmic sea. But it won't be traveling alone. Both Voyager spacecraft carry something special, a golden record. The Voyager Golden Record is a 12-inch disc made of gold-plated copper. It was designed to survive for billions of years in space, protected from the harsh environment by an aluminum cover. On the record are sounds and images from Earth, greetings in 55 languages, music from different cultures and eras, the sound of wind, rain, thunder, and waves, the songs of whales and birds, the cry of a newborn baby, the heartbeat of a human being. There are also images, pictures of Earth, of our continents and oceans, images of animals, plants, and people, diagrams showing our solar system and our place in the galaxy, instructions for how to play the record, written in symbols designed to be understood by beings who might find it millions of years from now. The record was created by a team led by the astronomer Carl Sagan. He saw it not just as a message to potential alien civilizations, but as a statement about who we are. A time capsule, a portrait of Earth in 1977. One of the most beautiful details about the record is what's hidden in the encoded audio. During the recording process, Anne Druyan, one of the team members, had her brainwaves and heartbeat recorded by an electroencephalogram. She was thinking about the history of Earth, the mysteries of the universe, and her newly discovered love for Carl Sagan. Those feelings, her thoughts about life and love and wonder, are encoded onto the record. They're traveling through space right now, carried by Voyager, drifting toward the stars. There's something poetic about that. A love story embedded in a message to the cosmos. A human heart beating silently in the void. Whether anyone will ever find the record is unknown. Space is unimaginably vast. The chances of another intelligent being intercepting Voyager are almost impossible to calculate. But that's not really the point. The point is that we tried. We reached out. We sent a message. We put a piece of ourselves into the darkness and said, "Here we are. This is who we were. This is what we loved." Even if no one ever finds it, the record represents something important about humanity, our curiosity, our hope, our desire to connect with something beyond ourselves. And now, as Voyager drifts through interstellar space, that message is farther from home than anything we've ever created. Back here on Earth, the data keeps coming. Every day, signals arrive at the Deep Space Network, the collection of giant radio antennas that NASA uses to communicate with distant spacecraft. The signals from Voyager are incredibly faint. By the time they reach Earth, they carry less energy than a billionth of a watt. But the antennas are sensitive enough to pick them up. Engineers process the signals, decode the data, and send it to scientists around the world. And in that data, the story of interstellar space continues to unfold. Scientists are still analyzing the hum. They're tracking the density of plasma as Voyager moves farther from home. They're watching for changes in cosmic ray levels, signs of activity from the sun, and unexpected features in the magnetic field. Every new measurement adds to our understanding. Every bit of data fills in another piece of the map. And for now at least, the spacecraft is stable. The instruments are working. The power is holding. No one knows exactly how much longer that will last. But the team at NASA is determined to squeeze every last drop of science from this mission. They've nursed Voyager back from the brink before. They'll do it again if they have to, because what Voyager is doing out there matters. It matters for science, for understanding the boundary of our home, for preparing for future missions that might one day travel even farther. But it also matters for something harder to measure, something about who we are and what we're capable of. When Voyager launched, humans had never left Earth's orbit for more than a few days. The internet didn't exist. Personal computers were a novelty. The world was a different place. And yet, in that world, a small team of engineers and scientists built a machine that would outlive them all, that would travel farther than anyone imagined, that would send back pictures and numbers and sounds from the edge of everything we know. That's an achievement worth celebrating, not just because of the science, but because of what it says about human ambition, about our refusal to accept limits, about our drive to explore, even when the destination is beyond our reach. Voyager 1 is the farthest thing we've ever sent into the universe, and it's still out there, still moving, still listening. And as long as its signal reaches Earth, we'll be listening too. The heliosphere is more than just a boundary. It's a shield. Inside it, we're protected. The sun's magnetic field and the constant outflow of the solar wind create a kind of armor around our entire solar system. This armor blocks most of the cosmic rays that flood through the galaxy. High-energy particles that could damage DNA, fry electronics, and pose serious risks to anything alive. Earth has its own protection too. Our magnetic field deflects charged particles. Our atmosphere absorbs radiation. We're wrapped in layers of defense that we barely notice most of the time. But if you were floating in interstellar space, outside the heliosphere, you'd be exposed to much higher levels of radiation. The cosmic ray flux is significantly greater out there, and there's nothing to stop those particles from passing through your body. This is one of the reasons Voyager's measurements matter for the future of human space exploration. If we ever send astronauts beyond the heliosphere, if we ever try to reach another star, we'll need to know what kind of environment they'll face. How intense is the radiation? How does it change over distance? What kinds of particles are most dangerous? Voyager is answering those questions right now. Before the Voyagers crossed the heliopause, all our knowledge about cosmic rays and interstellar radiation came from indirect measurements. We could detect particles that made it through the heliosphere and reached Earth. We could study the damage they caused to spacecraft closer to home. But we couldn't measure the source directly. Now we can. Voyager 1's instruments show that cosmic ray levels outside the heliosphere are roughly 40% higher than inside. That's a significant increase. It means any spacecraft traveling beyond the sun's protective bubble will need better shielding, more robust electronics, and careful planning to protect both machines and humans. It also means that the heliosphere itself is more important than we realized. It's not just a boundary on a diagram. It's a real physical shield that makes life in this solar system possible. Without the heliosphere, Earth would be bathed in far more high-energy radiation. Life might still exist, but it would face constant challenges from particle bombardment. Our technology would be more vulnerable. Our biology would be under greater stress. The sun protects us without us even noticing, and Voyager is helping us understand how. There's another side to this story. The interstellar medium isn't just a hazard. It's also a clue. The gas and dust floating between the stars carry information about the history of our galaxy. Every atom out there has a story. It was forged in the heart of a star, expelled in a supernova, scattered across space, mixed with other material, drifted for millions or billions of years. By studying the composition of the interstellar medium, scientists can learn about stellar evolution, how stars are born, how they live, how they die, and what they leave behind. Voyager can't measure every property of the interstellar medium. Its instruments are limited, but what it can measure adds to the picture. The density fluctuations it detects tell us about turbulence in the gas. The magnetic field direction tells us about the large-scale structure of the galaxy. The particle counts tell us about the balance between solar and galactic forces. All of this feeds into models that try to describe how the Milky Way works, how material flows through it, how stars form from collapsing clouds, how the galaxy evolves over billions of years. Voyager is just one tiny probe in an unimaginably vast system, but it's the only one we have out there, and the data it sends back has value far beyond its size. Let's slow down and appreciate the scale of what we're talking about. The Sun is about 93 million miles from Earth. That distance is called 1 astronomical unit. It's a handy measuring stick for distances in space. Jupiter is about 5 astronomical units from the Sun. Saturn is about 10. Neptune, the most distant planet, is about 30. Voyager 1, as of right now, is about 170 astronomical units from the Sun. That's more than 5 times farther than Neptune, more than 3 times farther than the most distant dwarf planets. At that distance, sunlight takes more than 22 hours to travel from the Sun to Voyager, and a radio signal takes the same amount of time to make the trip. When engineers at NASA send a command to Voyager 1, they have to wait almost 2 full days to find out if it worked. Send a signal, wait 22 hours, receive a response, wait 22 more hours. That's nearly 45 hours for a single round trip. Imagine trying to fix a computer that's that far away. Every keystroke takes a day and a half to confirm. Every troubleshooting step takes nearly a week to complete. That's what the Voyager team does, patiently, methodically, with incredible care. And despite those challenges, they've kept the spacecraft alive for almost 50 years. Now let's think even bigger. 1 light year is the distance light travels in a year. It's about 6 trillion miles, or about 63,000 astronomical units. Voyager 1 is currently less than 1 light day from the Sun. It hasn't even traveled 1 light day yet, and a light day is just 1/365th of a light year. The nearest star to our Sun is Proxima Centauri. It's about 4.2 light years away. That's over 265,000 astronomical units. At its current speed, Voyager 1 would take about 73,000 years to travel that distance. 73,000 years. That's longer than modern humans have existed. Longer than all of recorded history. Longer than the rise and fall of every civilization we've ever known. And that's just to reach the nearest star. The galaxy contains hundreds of billions of stars, spread across a disk more than 100,000 light-years wide. Voyager will never reach another star system in any meaningful sense. It will drift through the galaxy for millions of years, but the chances of it actually passing close to another sun are essentially zero. This is the reality of interstellar travel. The distances are so vast, the timescales so long, that even our fastest spacecraft are barely moving compared to the size of the universe. But that doesn't make Voyager's journey meaningless. The spacecraft doesn't need to reach a destination to have value. Its value is in what it's teaching us right now, about the heliosphere, about interstellar space, about the structure of our cosmic neighborhood. And its value is also symbolic. It represents the furthest reach of human curiosity, the longest arm we've ever extended into the darkness. Even when it falls silent, it will keep moving. A small, cold piece of Earth drifting through the stars, carrying our message, carrying our hopes, carrying the golden record with its sounds of home. That matters, not because anyone will find it, but because we sent it. Let's talk about what Voyager 2 has added to the story. Voyager 2 launched about 2 weeks before Voyager 1, but it took a slower, more winding path through the solar system. It visited Jupiter and Saturn like its twin, but it also flew past Uranus and Neptune. Those extra gravity assists pushed it into a different trajectory, one that carried it outward at a slower speed and in a different direction. By 2018, Voyager 2 had caught up in terms of distance from the heliosphere's edge, and in November of that year, it crossed the heliopause. This was a big deal for scientists. Now they had 2 data points instead of 1. 2 spacecraft measuring interstellar space from 2 different locations, and the results were illuminating. Voyager 2's crossing was different from Voyager 1's. When Voyager 1 crossed the boundary in 2012, the change was sudden. Cosmic ray levels jumped sharply. Solar particle counts dropped almost to zero. The transition happened over a very short distance. Voyager 2's experience was more gradual. The rise in cosmic rays was slower. The drop in solar particles was smoother. The boundary felt less like a wall and more like a slope. This told scientists something important. The heliopause is not uniform. It doesn't look the same in all directions. It bends and flexes and changes shape depending on where you are and what the sun has been doing. In the direction Voyager 1 traveled, the boundary was sharp. Maybe because the interstellar wind was pressing harder in that region. Maybe because solar activity at the time had compressed the edge. In the direction Voyager 2 traveled, the boundary was softer. The pressure balance was different. The transition was more drawn out. Having two spacecraft in interstellar space gives scientists a way to study these differences. They can compare the data, look for patterns, test their models against real observations from two separate locations. It's still not enough to map the entire heliosphere. That would require dozens of spacecraft, spread out in all directions. But two is infinitely better than one. And both Voyagers continue to send back data. Both continue to reveal new surprises. One of the ongoing mysteries involves the magnetic field. Before Voyager 1 crossed the heliopause, many scientists expected the magnetic field direction to change dramatically. Inside the heliosphere, the field is shaped by the sun. It spirals outward, following the rotation of the sun's magnetic poles. Outside the heliosphere, the field should be shaped by the galaxy. It should point in a completely different direction, set by the large-scale structure of the Milky Way. But when Voyager 1 crossed the boundary, the magnetic field direction barely changed at all. It tilted a little. It got a bit stronger. But it didn't flip the way models predicted. This was confusing. How could the spacecraft be in interstellar space, surrounded by galactic material, but still feel a magnetic field that looked like it came from the sun? Several ideas have been proposed. One is that the boundary itself is so complex, with layers and folds and mixing zones, that the magnetic field takes time to transition from solar to galactic. Another is that the interstellar field happens to be aligned in a similar direction by coincidence. Voyager 2 added more complexity to the puzzle. Its magnetic field readings were slightly different from Voyager 1's. The direction was shifted. The strength was different. The pattern didn't match perfectly. This is the kind of mystery that keeps scientists up at night. And it's exactly the kind of thing the Voyagers were designed to explore. Except, of course, they weren't really designed for this. Their original mission was to photograph planets. The interstellar part was an afterthought, a bonus, a happy accident. The fact that they're still producing meaningful data about magnetic fields in interstellar space is a testament to both the engineering that went into them and the creativity of the scientists who keep finding new uses for old instruments. There's a lesson in that. Sometimes the best discoveries come from missions that outlive their original purpose. Sometimes the real magic happens after the planned work is done. The Voyagers have been in their extended mission longer than they were in their primary mission, and the extended mission has taught us things we never could have learned any other way. Let's take a moment to think about what we've learned so far. We've learned that the heliopause is real. It's not just a theoretical line on a chart. It's a physical boundary where conditions change dramatically. We've learned that crossing the boundary is not simple. The transition can be sudden or gradual depending on location. The shape of the heliosphere is not a perfect sphere. It's lumpy and asymmetric. We've learned that interstellar space is not empty. It's filled with plasma, magnetic fields, cosmic rays, and turbulence. The density is higher than expected in some places. The environment is more dynamic than scientists imagined. We've learned that the sun's influence extends far beyond the planets. Even at the edge of the heliosphere, solar events can cause ripples that travel outward and affect the boundary. The heliosphere breathes. It responds. It changes. we've learned that cosmic ray levels are significantly higher outside the heliosphere. This has implications for future exploration. Any spacecraft or astronaut venturing beyond the sun's bubble will face increased radiation. And we've learned that there's still so much we don't know. Every answer raises new questions. Every measurement reveals new complexity. The more data we collect, the more we realize how little we understood before. That's the nature of exploration. You think you're heading toward answers, but what you find is more questions. And that's okay. That's how science works. The goal is not to know everything. The goal is to know more than we did yesterday. Voyager is helping us do that. One faint signal at a time. Now let's look at the instruments that make all this possible. When Voyager launched, it carried a suite of scientific instruments designed to study the outer planets. Cameras for taking pictures, spectrometers for analyzing light, magnetometers for measuring magnetic fields, particle detectors for counting cosmic rays and plasma. Most of these instruments have been turned off. The cameras were shut down in 1990, after the famous pale blue dot photo was taken. Other instruments were disabled as power decreased and the spacecraft moved beyond their useful range. What's left is a small set of tools focused on particles and fields. The cosmic rays subsystem counts high-energy particles from the galaxy. It tracks how cosmic ray levels change over time and distance. The low-energy charged particle instrument measures particles with lower energies. It helps distinguish between solar particles and galactic particles. The magnetometer measures the strength and direction of magnetic fields around the spacecraft. It's been providing continuous data since launch. And the plasma wave system listens for electric and magnetic fluctuations in the plasma. It's the instrument that detected the hum of interstellar space. These four instruments are the eyes and ears of Voyager in interstellar space. They can't take pictures. They can't analyze atmospheric composition. But they can feel the environment around them in ways that reveal the structure of the cosmos. The fact that they're still working after nearly 50 years is remarkable. The engineers who designed them built in margins for uncertainty. They used simple, robust components. They tested everything relentlessly, and it paid off. These instruments have far exceeded their design life. They've operated in conditions they were never meant to face, and they keep delivering science. Eventually, they'll go quiet. The power will drop too low. The circuits will fail. The signal will fade. But until that happens, every day counts. Every bit of data is precious, and the teams on Earth are working hard to make sure nothing is wasted. The Deep Space Network plays a critical role in this. The Deep Space Network is a collection of large radio antennas located at 3 sites around the world: Goldstone in California, Madrid in Spain, Canberra in Australia. These sites are spaced roughly 120 degrees apart around the globe. That means at any given time, at least one of them can see any point in the sky. No matter where Voyager is in its orbit around the Sun, no matter what time of day it is, one of the antennas can listen. The antennas are huge. The largest dish at each site is 70 meters across, about 230 feet. These giant ears can pick up signals so weak that they carry less energy than a flashlight battery produces in 1 billion years. When Voyager transmits, its signal is about 20 watts. By the time that signal reaches Earth, after traveling 15 billion miles through space, it's spread out so thin that the power arriving at the antenna is measured in trillionths of a watt. But the antennas are sensitive enough to detect it. Engineers amplify the signal, filter out the noise, and decode the data. It's an incredible feat of engineering. And it happens every day for both Voyager spacecraft. The Deep Space Network doesn't just talk to Voyager. It communicates with dozens of missions throughout the solar system. Mars rovers, Jupiter probes, spacecraft studying asteroids and comets. But Voyager holds a special place. It's the most distant target, the faintest signal, the hardest to reach, and every time a transmission comes through, it's a reminder that the spacecraft is still out there, still alive, still connected to home. Let's consider what the future might hold. Within the next few years, Voyager 1 will likely run out of power for science operations. The generators will keep producing electricity for a while longer, but not enough to run instruments. At some point, NASA will have to decide which systems to keep alive and which to shut down. Eventually, the spacecraft will go silent. The transmitter will stop. The signal will fade. But the physical spacecraft will keep moving. There's no air to slow it down. No friction to wear it out. Just the infinite emptiness of space. Voyager 1 will drift outward at 17 kilometers per second. Year after year, century after century, millennium after millennium. In about 300 years, it will reach the inner edge of the Oort cloud. This vast shell of icy objects marks the true outer boundary of the solar system, the region where the sun's gravity barely holds things in orbit. Crossing the Oort cloud will take tens of thousands of years, maybe 30,000, maybe more. After that, Voyager will be truly between the stars. Floating in the deep emptiness of interstellar space with nothing but the faint glow of distant suns to light its way. In about 40,000 years, it will pass within about 1.7 light-years of a small, dim star called AC, plus 793888. That's the closest it will come to another sun for a very long time. But passing within 1.7 light-years doesn't mean much. That's still about 10 trillion miles. Voyager won't see the star, won't feel its gravity, won't notice it at all. It will just keep drifting, silently, endlessly. The spacecraft is so small and the galaxy is so big that the chances of Voyager ever hitting anything are essentially zero. It could drift for billions of years without encountering a single object. It will outlast the Earth, outlast the sun, outlast everything we know. Long after our planet is gone, Voyager will still be out there, a cold, silent messenger carrying the golden record through the dark. Whether anyone will ever find it is impossible to say. Space is vast beyond comprehension. The galaxy contains hundreds of billions of stars, spread across distances that make our entire solar system look like a speck of dust. The odds of another civilization intercepting Voyager are vanishingly small. It would require a species with the technology to detect a tiny, cold object drifting through space. It would require that they happen to be in the right place at the right time, somewhere along Voyager's endless path. But the odds are not zero, and the people who made the golden record knew that. They weren't sending a message because they expected a reply. They were sending a message because it was worth sending, because it said something about who we are. The record contains greetings in 55 languages, not because aliens would understand all of them, but because it represents the diversity of human culture, the richness of our world. It contains music from different eras and traditions. Bach, Beethoven, Chuck Berry, traditional songs from cultures around the globe. Not because aliens would appreciate the melodies, but because music is one of the most human things we do. It contains sounds of nature, wind, rain, thunder, birds, whales. Because we are not separate from our planet, we are part of it. And it contains Anne Druyan's heartbeat and brainwaves, her thoughts of love and wonder recorded at a moment of profound emotion. All of this is traveling through space right now, carried by Voyager. Moving away from home at 10 miles every second, it's the farthest our hearts have ever reached. Some people call the golden record a message in a bottle, thrown into the cosmic ocean with no expectation of a reply. But maybe it's more than that. Maybe it's a mirror, a way of seeing ourselves from the outside, a reminder of what we value, what we love, what we hope for. The record wasn't made for aliens, not really. It was made for us, to show that even in the vastness of space, even facing the certainty of silence, we still reach out. We still try. We still hope. That's worth something. Even if no one ever finds it, because the act of sending matters, the effort of creating matters, the choice to include our best selves, our most beautiful creations, our most hopeful dreams, that matters. Voyager carries all of that into the darkness, and in doing so, it carries a piece of every one of us. Right now, as you listen to this, Voyager 1 is still transmitting. It's still sending back data about the plasma density around it, still measuring cosmic rays, still feeling the magnetic field. The signal is faint. It takes nearly a full day to reach Earth, but it's there. And scientists are still listening. They're analyzing every measurement, building better models of the heliosphere, refining their understanding of interstellar space. This work will continue until the spacecraft goes silent. And even after that, the data already collected will be studied for decades to come. Voyager's legacy is not just in what it discovered. It's in the questions it raised, the mysteries it revealed, the foundation it laid for future exploration. Someday, other spacecraft will follow in Voyager's path. They'll be faster, more advanced, better equipped. But Voyager was first. It crossed the heliopause when no one else could. It measured interstellar space when no one else had. It sent back data from a place we had only imagined. That makes it special. That makes it worth celebrating. And that's why we're talking about it now. Because even in the age of rovers on Mars and telescopes peering at distant galaxies, this little spacecraft from 1977 is still doing something no other mission can do. It's showing us the edge of our world and what lies beyond. There's something deeply comforting about knowing Voyager is out there. In a world that often feels chaotic, divided, and uncertain, this little spacecraft represents something enduring, something hopeful, a project that started decades ago, that has outlived many of the people who built it, and that continues to push forward, one slow kilometer at a time. It doesn't care about politics or borders or conflicts. It just keeps going, quietly, steadily, through the vast emptiness of space. And in that steadiness, there's a kind of peace. The engineers who maintain Voyager today work in a room at the Jet Propulsion Laboratory in California. It's not a glamorous place. The equipment is old. The procedures are familiar. The work is methodical. But every day, they're connected to something extraordinary. A machine farther from Earth than anything humans have ever built. A signal from the edge of the solar system. A whisper from the void. That connection is precious, and everyone who works on the mission knows it. They know that when Voyager finally goes silent, there will be nothing to replace it. No other spacecraft is heading that direction. No other mission is planned for interstellar space in the near future. When the signal stops, the window closes, and so they work to keep it open as long as possible, squeezing every watt of power, nursing every aging circuit, listening for every faint transmission. It's a labor of love, and it shows in the care they bring to the work. Let's talk about some of the challenges they've faced. Over the years, Voyager has experienced all kinds of problems: hardware failures, software glitches, unexpected shutdowns, communication blackouts. Each time, the team has found a way to fix it, sometimes with clever workarounds, sometimes with brute force troubleshooting, sometimes with solutions that took months to develop and test. One of the most dramatic episodes happened in 2023. Voyager 1 suddenly started sending back data that made no sense. The signals were garbled. The numbers didn't match anything the spacecraft should be producing. For weeks, no one knew what was wrong. The spacecraft was too far away to diagnose directly. Every command took a day and a half to reach it. Every response took another day and a half to come back. Engineers had to work like detectives. They analyzed the garbled data. They compared it to simulations. They tested theories one at a time. Eventually, they figured it out. A memory chip in one of the onboard computers had failed. Maybe from a cosmic ray strike, maybe from simple age. The chip was corrupted, and it was causing the spacecraft to send garbage instead of real data. The fix was ingenious. They couldn't replace the chip. They couldn't physically touch the spacecraft. But they could move the affected code to a different part of memory. They wrote new software. They uploaded it piece by piece. They waited through the agonizing delays, and in April of 2024, it worked. Voyager 1 started sending real data again. The mission was saved, at least for now. But the episode was a reminder of how fragile the situation is. The spacecraft is old. The hardware is wearing out. Every problem could be the last one. And there's no backup, no spare Voyager waiting to take over. When this one dies, that's it. That's part of what makes the mission so poignant. It's not just about science. It's about time. About the fleeting window we have to explore this region of space before our only instrument falls silent. Every day that Voyager keeps transmitting is a gift, and the team treats it that way. Let's explore the concept of interstellar space a bit more deeply. When we say interstellar space, we mean the region between stars. The space that's not dominated by any single sun. The vast emptiness that makes up most of the volume of our galaxy. But emptiness is a relative term. Interstellar space is not completely empty. It's filled with the interstellar medium, a thin soup of gas, dust, cosmic rays, and magnetic fields. Most of this material is hydrogen and helium, the two lightest elements. These atoms float through space at incredibly low densities. In some regions, you might find only one atom per cubic centimeter. In others, the density can be a bit higher. Compare that to the air you're breathing right now. At sea level on Earth, there are about 25 quintillion molecules per cubic centimeter. That's a number with 19 zeros after it. Interstellar space is unimaginably thin by comparison. But over the vast distances between stars, even this thin material adds up. It absorbs light. It shapes magnetic fields. It provides the raw material for new stars and planets. Voyager is floating through this material right now, drifting through a cloud of atoms so sparse that you could wave your hand through it and never feel a thing. But the spacecraft's instruments can feel it. They can measure the tiny fluctuations in the plasma. They can count the particles striking the detectors. They can sense the faint hum of the interstellar medium. That hum, the one discovered in 2017, is one of the most remarkable findings of the mission. It's the sound of the galaxy itself, the background noise of the cosmos. Imagine standing in a forest at night. At first, you might think it's completely silent. But if you listen closely, you start to hear things. The rustle of leaves, the chirp of insects, the distant call of an owl. Interstellar space is like that. At first glance, it seems empty and quiet. But listen closely enough, and you start to hear the universe breathing. Voyager is doing that listening for us. And what it hears is changing what we understand about our cosmic neighborhood. The interstellar medium is not uniform. It has structure, patterns, regions of different density and temperature. Near the Sun, there's a feature called the local interstellar cloud. It's a wisp of slightly denser gas, about 30 light-years across, drifting through our region of the galaxy. Our solar system is probably inside this cloud right now, or at least very close to its edge. The Voyagers are helping us understand exactly where we are in relation to this structure. Beyond the local interstellar cloud lies the local bubble, a much larger cavity of unusually hot, thin gas. This bubble was carved out by ancient supernova explosions millions of years ago. The explosions swept away the surrounding material, leaving behind a void that the Sun has been traveling through for millions of years. Understanding these structures matters for several reasons. First, it affects how we interpret astronomical observations. The interstellar medium between us and distant stars can absorb and scatter light. Knowing what's nearby helps us correct for these effects. Second, it has implications for the history of life on Earth. The density of the interstellar medium affects how much cosmic radiation reaches our planet. Changes in this environment could have influenced evolution over geological timescales. Third, it matters for future exploration. Any spacecraft heading to another star will have to travel through interstellar space. Knowing what's out there helps us plan for the journey. Voyager can't answer all these questions. It's just one probe, traveling in one direction, measuring one path through the cosmos. But it's giving us a ground truth, a direct measurement of what the interstellar medium actually looks like, rather than what our models predict. And that ground truth is invaluable. It's the foundation on which future exploration will be built. Let's zoom out and think about the bigger picture. The Voyager mission represents a turning point in human history. It's the first time we've sent anything beyond the influence of our Sun. The first time we've touched interstellar space. That might not seem like a big deal in practical terms. We can't visit interstellar space ourselves. We can't build colonies there. We can't mine resources or establish trade routes. But symbolically, it matters enormously. For thousands of years, humans have looked up at the stars and wondered. We've told stories about them. We've navigated by them. We've dreamed of reaching them. And now, for the first time, we have. It's a small step. Voyager is tiny compared to the distances involved. It will take tens of thousands of years to get anywhere close to another star. But it's a step. A real, physical presence beyond the boundary of our home. That's something new in the history of our species. Something that changes our relationship with the cosmos. We are no longer entirely confined to our solar system. A piece of us has escaped. A piece of us is out there drifting among the stars. That piece carries our message, our music, our hopes. And in that sense, Voyager represents the best of what we are. The part of us that reaches beyond ourselves. The part that refuses to accept limits. The part that wants to know what's out there, even if we can never see it with our own eyes. That's worth honoring. That's worth remembering. Because even in our darkest moments, even when the world seems small and cruel and hopeless, Voyager is out there, still moving, still carrying our dreams into the void. And that's something beautiful. Now let's return to the science. One of the ongoing puzzles about the heliosphere is its shape. For a long time, scientists thought the heliosphere was stretched out like a comet, a rounded front facing the direction the sun is moving through space, a long tail trailing behind. This model made intuitive sense. The sun is plowing through the interstellar medium at about 23 kilometers per second. The solar wind rams into the incoming material, gets deflected, and flows around the obstacle. Just like water flowing around a rock in a stream. But observations have complicated this picture. Data from the Interstellar Boundary Explorer, a satellite orbiting Earth, suggested that the heliosphere might be more spherical than expected. The material behind the sun, in the so-called heliotail, wasn't as stretched out as models predicted. Some scientists proposed a completely different shape, a kind of croissant or crescent. Others suggested a four-lobed clover pattern. The truth is, we don't know for sure. The heliosphere is too big to photograph directly. We can only infer its shape from indirect measurements. And that's where the Voyagers come in. By crossing the heliopause at two different locations, Voyager 1 and Voyager 2 give us points of reference. They tell us where the boundary is in at least two directions. Voyager 1 crossed at about 122 astronomical units from the Sun, traveling roughly north of the ecliptic plane. Voyager 2 crossed at about 119 astronomical units, traveling south. These numbers are close but not identical, and the conditions at each crossing were different. This tells us that the heliosphere is not perfectly symmetric. It's squashed or stretched in different directions, depending on the pressure from the interstellar medium. Future missions might help clarify the picture. But for now, the Voyagers provide our best direct evidence of the heliosphere's edge. There's another mystery that Voyager is helping to explore: the nature of cosmic rays. Cosmic rays are high-energy particles, mostly protons, that zoom through the galaxy at nearly the speed of light. They come from violent events like supernova explosions and black hole jets. Inside the heliosphere, the sun's magnetic field and the solar wind help block these particles. They deflect incoming cosmic rays, scatter them, and reduce the number that reach the inner solar system. But outside the heliosphere, that protection disappears. The cosmic ray flux is much higher. Voyager has been tracking cosmic rays since before it crossed the heliopause, and what it found confirmed the basic picture. Cosmic ray levels jumped when the spacecraft entered interstellar space. But the details are more interesting. The increase wasn't uniform across all energy levels. Some particles showed bigger jumps than others, and the pattern varied over time. This tells scientists something about how cosmic rays interact with the heliosphere, how they're scattered, how they penetrate, how they behave at different energies. These details matter for understanding the environment astronauts would face on long-duration missions. The more we know about cosmic rays, the better we can protect future explorers. Voyager is also watching for something called anomalous cosmic rays. Anomalous cosmic rays are particles that started out as neutral atoms in the interstellar medium. They drifted into the heliosphere, got ionized by sunlight or the solar wind, and were then accelerated to high energies by the sun's magnetic field. These particles were expected to show up in large numbers at the heliopause. Models predicted they would pile up there like water behind a dam. But when Voyager 1 crossed the boundary, the expected pile-up wasn't there. The anomalous cosmic rays dropped off before the spacecraft reached interstellar space. This was a surprise. It didn't match predictions, and scientists are still trying to figure out why. One idea is that the particles are escaping along magnetic field lines that stretch beyond the heliopause. Another is that the acceleration mechanism doesn't work the way models assumed. Either way, it's a reminder that the real universe is messier than our models, and that direct observations, like those from Voyager, are essential for testing our understanding. Let's talk about what comes next. Right now, there are no spacecraft on their way to interstellar space. The Voyagers are the only ones that have made it, and both are approaching the end of their operational lives. But that doesn't mean the exploration of interstellar space is ending. It's just pausing. Several concepts for future missions have been proposed. One idea is called the interstellar probe. It would be a dedicated mission to explore the heliosphere and the interstellar medium. Faster than Voyager, better equipped, designed from the start for this kind of exploration. The interstellar probe would launch sometime in the next decade or two. It would use advanced propulsion, possibly a gravity assist from the Sun, to reach speeds of about 90 kilometers per second. That's 5 times faster than Voyager. At that speed, it could reach the heliopause in about 15 years. And it would carry a suite of instruments designed specifically for interstellar science. The mission is still in the planning stages. It hasn't been funded or approved, but the concept is being studied seriously by NASA and other agencies. Another idea is even more ambitious. A fleet of tiny spacecraft, propelled by laser sails, traveling at a significant fraction of the speed of light. This concept is called breakthrough starshot. The idea is to use powerful ground-based lasers to accelerate gram-scale probes to speeds of about 20% the speed of light. At that speed, the probes could reach the nearest star system, Alpha Centauri, in about 20 years. It sounds like science fiction, and in many ways, it still is. The technology doesn't exist yet. The engineering challenges are enormous. The costs are staggering, but serious scientists and engineers are working on it. And the basic physics seems possible. If it ever works, it would represent a completely different approach to interstellar exploration. Instead of one big spacecraft making a slow journey, you'd have thousands of tiny probes racing through space, gathering data, and sending it back to Earth. Whether any of this happens in our lifetimes is uncertain. The distances are so vast, the challenges so great, that progress will be slow. But the fact that people are thinking about it, planning for it, dreaming of it, that itself is significant. Voyager showed us that interstellar space is real, that we can reach it, that we can learn from it. Now the question is, what do we do next? For the moment, the answer is simple. We keep listening to Voyager. We squeeze every last bit of data from its aging instruments. We learn as much as we can before the signal fades, and we dream of what comes after. The human desire to explore is ancient. It predates civilization. It predates language. It's woven into the fabric of who we are. Every generation has pushed a little farther, over the next hill, across the next ocean, beyond the next horizon. Now the horizon is interstellar space, the edge of everything we've ever known. And Voyager is showing us the way. It's easy to feel small when you think about the scale of the cosmos. The distances are so vast, the timescale so long, that human lives seem like flickering sparks in an endless night. But there's another way to look at it. We are the only species on Earth that has sent a spacecraft beyond the solar system. The only species that has recorded its music, its languages, its hopes, and flung them into the void. Out of all the billions of creatures that have ever lived on this planet, we are the ones who reached for the stars. That's not small, that's remarkable. And Voyager is the proof. It's a monument to human ingenuity, to patience, to the refusal to accept limits. Every bit of data it sends back is a reminder of what we're capable of when we work together, when we dream big, when we refuse to give up. That's the real legacy of the Voyager mission. Not just the science, though the science is incredible, but the spirit behind it. The belief that exploration is worth doing, even when the destination is beyond our reach. That spirit is alive today, in the engineers who keep Voyager running, in the scientists who study its data, in the dreamers who plan future missions to the stars, and in everyone who looks up at the night sky and wonders what's out there. Voyager is out there right now, moving through the darkness, carrying our message. And as long as we remember that, the mission continues, not just in the spacecraft itself, but in all of us. Because Voyager isn't just a machine, it's an idea. The idea that we can reach beyond ourselves, that we can touch the unknown, that even in the face of infinite vastness, we can send something into the darkness and say, here we are. That idea will outlive any spacecraft, any mission, any generation. It's part of who we are, and it always will be. The region Voyager is traveling through now is strange and unfamiliar. It's not the peaceful void that science fiction often imagines. It's not a calm sea of emptiness stretching forever in all directions. It's active, dynamic, filled with subtle forces and quiet interactions. The interstellar wind, a flow of gas from nearby stars, pushes against the heliosphere and shapes its boundary. The galactic magnetic field threads through space, bending and twisting in patterns we're only beginning to understand. Cosmic rays zip through the darkness, carrying energy from explosions that happened millions of years ago. And somewhere in the middle of all this, Voyager drifts, a tiny piece of Earth, a messenger from home. The spacecraft can't see this environment the way we see the world around us. It has no eyes in the traditional sense. Its cameras were turned off decades ago, but it can feel the environment. Its instruments detect changes in particle counts, shifts in magnetic field direction, fluctuations in plasma density. From these measurements, scientists build a picture of what the space around Voyager looks like. Not a photograph, but a map of forces and particles, and that map keeps surprising us. One of the recent surprises came in 2020. Both Voyager spacecraft detected an increase in plasma density that didn't match any predictions. Inside the heliosphere, density drops as you move, away from the sun. That makes sense. The solar wind spreads out as it travels, becoming thinner and thinner. But outside the heliosphere, Voyager found the opposite. Density was increasing as the spacecraft moved farther from home. This was unexpected. The interstellar medium should be relatively uniform over these scales. There shouldn't be such a sharp gradient. Several theories have been proposed. One idea is that we're seeing the hydrogen wall, a region where neutral hydrogen from the interstellar medium piles up at the edge of the heliosphere. The incoming gas gets slowed and compressed as it interacts with the solar wind, creating a denser layer. Another idea involves magnetic effects. The interstellar magnetic field might be concentrating charged particles in certain regions, creating pockets of higher density. A third possibility is that Voyager is passing through a local cloud or filament of denser gas. The interstellar medium isn't perfectly smooth. It has structures on many scales. The spacecraft might simply be moving through one of these structures. We don't know which explanation is correct. Maybe it's a combination of all three. Maybe it's something else entirely. That's the nature of exploration. You go somewhere new, and you find things you didn't expect. Things that don't fit your models. Things that force you to rethink what you thought you knew. Voyager is doing that right now, and it will keep doing it until the signal stops. Let's think about what Voyager means for the future of astronomy. For most of human history, our knowledge of space came from looking. We pointed telescopes at the sky and collected light. We measured wavelengths and frequencies. We built images and spectra. This approach has been incredibly successful. It's given us everything from the structure of galaxies to the composition of distant planets. But it has limits. You can only learn so much from a distance. Some properties of space can only be measured by being there. Voyager represents a different approach. In situ exploration, going to a place and measuring it directly. This kind of exploration is common for planets and moons. We've sent rovers to Mars, probes to Jupiter, landers to Titan. We know what these places are like because we've touched them. But no one had ever done that for interstellar space, until Voyager. Now we have direct measurements of what the environment beyond the heliosphere is like. Not inferences from distant observations, actual numbers from actual instruments in actual interstellar space. This changes things. Models that were built on theoretical assumptions can now be tested against real data. Ideas that seem reasonable on paper can be checked against what Voyager actually found. And in many cases, the models were wrong. The reality was more complex, more surprising, more interesting than anyone predicted. That's the value of in situ exploration. It keeps us honest. It forces us to confront the universe as it actually is, not as we imagine it to be. Future missions to interstellar space will build on what Voyager has taught us. They'll refine our understanding. They'll answer new questions. But Voyager was first. It blazed the trail. And everything that follows will owe a debt to this little spacecraft. From 1977, there's a kind of poetry in the Voyager mission. It started as a practical project, a way to take advantage of a rare planetary alignment, a chance to photograph the outer planets before the opportunity passed. But it became something more. As the years passed and the spacecraft kept going, the mission evolved. It stopped being about planets and started being about boundaries, about limits, about what lies beyond. Now, nearly 50 years later, Voyager represents something almost spiritual, a human presence in the cosmos, a connection to something larger than ourselves. The golden record captures that spirit perfectly. It's not a scientific instrument. It doesn't measure anything. It doesn't send back data. It's a gesture, a wave, a hello from Earth. The record contains sounds and images that were chosen not because they were important, but because they were beautiful, because they represented who we are at our best. There's a recording of a baby's first cry, the sound of a mother comforting her child, laughter, a kiss. There's music that spans cultures and centuries, Bach's Brandenburg Concerto, Beethoven's Fifth Symphony, Chuck Berry's Johnny B. Good, traditional songs from China, India, Africa, Australia. There are images of Earth, mountains and oceans, cities and forests, people of all ages and backgrounds. All of this is traveling through interstellar space right now, moving away from home at 10 miles every second. It's a time capsule, a portrait of Earth in 1977, a snapshot of a moment in human history, and it will last longer than anything else we've ever made. The record is designed to survive for 1 billion years, long after every building on Earth has crumbled, long after every written document has faded, long after every digital file has corrupted. The golden record will still be out there, drifting through the darkness, waiting. Whether anyone will ever find it is unknowable. The universe is vast beyond comprehension. The chances of interception are vanishingly small. But that's not the point. The point is that we tried. We reached out. We said, here we are. This is what we love. This is who we are. And in making that gesture, we revealed something about ourselves. We are a species that dreams, that hopes, that refuses to believe we're alone in the cosmos. Voyager carries that dream into the void. And as long as it's out there, that dream is alive. Carl Sagan, who led the team that created the golden record, once said something beautiful about it. He said the record was like a message in a bottle, cast into the cosmic ocean. We don't know if anyone will ever find it. We don't know if anyone is out there to find it. But the act of sending it says something important about us, about our willingness to hope, about our desire to connect. The bottle is still floating. The message is still traveling. And somewhere in the darkness, Earth's voice echoes through the stars. The boundary that Voyager crossed is not just a physical transition, it's a conceptual one. Inside the heliosphere, we're home. The sun dominates. Its light warms the planets. Its wind fills the space. Its gravity holds everything in orbit. Outside the heliosphere, the rules change. The sun becomes just another star, one of hundreds of billions in the galaxy. Its influence fades into the background noise of the cosmos. Voyager made that transition. It stepped from home into the wider universe. Amika. And it's still connected to us, still sending back reports, still telling us what it's like out there. That connection won't last forever. The power is fading. The instruments are aging. Someday soon, the last transmission will arrive, and then silence. But for now, the line is open, and we're listening. Let's think about what the sun means in this context. The sun is not just a source of light and heat. It's a presence, a force that shapes everything around it. The solar wind, that constant stream of charged particles, creates a bubble that extends far beyond the planets. This bubble, the heliosphere, is the sun's domain, its territory, its kingdom. Inside this bubble, the sun's magnetic field organizes everything. Charged particles follow its curves. Cosmic rays are deflected. The entire region is sculpted by solar forces. The heliosphere is enormous. It stretches more than 100 times farther from the sun than Earth does. It encompasses all the planets, all the asteroids, all the comets that orbit close enough to feel the solar wind. But it has limits. At the heliopause, the solar wind finally runs out of steam. The pressure from outside, from the interstellar medium, equals the pressure from inside. And the sun's influence ends. Voyager crossed that limit. It passed from the sun's kingdom into neutral territory. In a very real sense, the spacecraft left home. Not in the sense of leaving Earth. That happened back in 1977. But in the sense of leaving the sun's protection, the sun's influence, the sun's care. Now Voyager is on its own, floating through a region where no star dominates, where the rules are set by the galaxy as a whole. That's a profound transition, and Voyager is the only human object to have made it. The heliosphere itself is constantly changing. Every 11 years, the sun goes through a cycle of activity. At solar maximum, the sun is more active. There are more sunspots, more flares, more eruptions. The solar wind is stronger. At solar minimum, the sun is quieter. The wind is weaker. The magnetic field is calmer. These cycles affect the heliosphere. When the sun is more active, the bubble expands. The heliopause pushes outward. Cosmic ray levels inside the heliosphere drop because the stronger wind blocks more particles. When the sun is quiet, the bubble contracts. The heliopause moves closer. Cosmic rays penetrate deeper into the solar system. Voyager has experienced multiple solar cycles during its journey. It watched the heliosphere breathe in and out. It felt the effects of solar storms that happened months or years earlier, the pressure waves that traveled outward and eventually reached the spacecraft at the edge of the bubble. This connection between the Sun and the distant heliosphere is one of the things that makes the region so dynamic. It's not a static boundary. It's a living edge, constantly responding to what the Sun does. And Voyager has had a front row seat to this process. Some of the most dramatic events in the Sun's cycle are coronal mass ejections. These are massive eruptions of plasma and magnetic field from the Sun's outer atmosphere. They blast outward at hundreds or even thousands of kilometers per second. When a coronal mass ejection hits Earth, it can cause geomagnetic storms. These storms disrupt satellites, damage power grids, and create beautiful auroras in the polar skies. But the effects don't stop at Earth. The ejected material keeps traveling outward. It passes Mars. It passes Jupiter. It reaches the outer planets and beyond. Eventually, months or years after the original eruption, the pressure wave arrives at the heliopause. Voyager has detected these events. It has felt the distant echoes of solar storms that happened long before the data reached Earth. The spacecraft is so far away that it experiences the Sun's activity on a time delay, like watching a slow-motion replay of events that happened ages ago. This gives scientists a unique perspective on how the Sun interacts with its environment. They can study the same events from multiple vantage points: Earth-based observations, spacecraft closer to the Sun, and finally, Voyager watching from the far edge of the heliosphere. The combination of these viewpoints creates a more complete picture than any single observation could provide. Let's consider the termination shock, another boundary that Voyager crossed years before reaching the heliopause. The termination shock is the point where the solar wind slows down from supersonic speeds. Inside this boundary, the wind is racing outward faster than sound waves can travel through it. It's a supersonic flow, but as the wind approaches the edge of the heliosphere, it runs into resistance. The interstellar medium pushes back. The wind starts to slow down. At the termination shock, the transition happens suddenly. The wind drops from supersonic to subsonic speeds. It gets compressed and heated. Its character changes. Voyager 1 crossed the termination shock in December of 2004 at a distance of about 94 astronomical units from the Sun. Voyager 2 crossed it in August of 2007 at about 84 astronomical units. The fact that these distances were different was significant. It showed that the termination shock is not a perfect sphere. It's closer to the Sun in some directions than others. In the direction Voyager 2 traveled, the shock was about 10 astronomical units closer. That's roughly 1 billion miles of difference, not a small amount. This asymmetry tells scientists something about the forces shaping the heliosphere. The interstellar wind doesn't push evenly in all directions. It compresses the heliosphere more in some places than others. The region between the termination shock and the heliopause is called the heliosheath. It's a thick layer of shocked, turbulent solar wind. The Voyagers spent years traveling through the heliosheath before reaching the heliopause. During that time, they measured the conditions in this strange transition zone. The heliosheath is not a calm place. The solar wind is compressed and jumbled. Magnetic fields twist and fold. Particles bounce around in complex patterns. Scientists used to think the heliosheath would be relatively simple, a smooth transition zone between the fast inner wind and the interstellar medium beyond. But Voyager showed it was much more complicated. There were unexpected features, regions of different density, magnetic anomalies, structures that didn't match predictions. The heliosheath turned out to be a wild, turbulent frontier, a place where the sun's influence is breaking down, but hasn't fully ended. After crossing the heliopause, Voyager entered interstellar space. But even there, the effects of the heliosphere aren't completely gone. The boundary is not a clean wall. It's more like a membrane. Some particles can leak through. Some fields can bend across. For example, the magnetic field direction that Voyager measured after crossing the heliopause didn't change as much as expected. It tilted slightly, but it didn't flip to a completely different orientation. This suggests that the boundary is more complex than a simple dividing line. There may be layers, mixing zones, regions where solar and interstellar influences overlap. Scientists call this the very local interstellar medium. It's the patch of space immediately outside the heliosphere, still influenced by our sun's presence, still shaped by the bubble's existence. Voyager is exploring this transition zone now, mapping its properties, measuring its quirks. Someday, the spacecraft will move beyond this region into truly pristine interstellar space. Space that has never felt the sun's touch. Space that belongs entirely to the galaxy. But that's still far in the future. For now, Voyager is in the in-between, the borderland, the edge of everything we know. There's a philosophical question that the Voyager mission raises. Where does the solar system end? It sounds like a simple question, but the answer depends on how you define the boundary. If you define the solar system by the heliosphere, then Voyager has already left. It crossed the heliopause in 2012. It's in interstellar space by that definition. But if you define the solar system by the sun's gravitational influence, then Voyager is still inside. The sun's gravity extends much farther than the heliosphere. It holds objects in orbit out to enormous distances. The Oort cloud, that vast shell of icy bodies surrounding the solar system, is held by the sun's gravity. It stretches from about 2,000 to 200,000 astronomical units from the sun. Voyager 1, at 170 astronomical units, hasn't even reached the inner edge of the Oort cloud. By this definition, it's still well inside the solar system. It will take about 300 years for Voyager to reach the Oort cloud, and tens of thousands of years to cross it. So which definition is correct? Is Voyager in interstellar space or not? The answer is both. It depends on what you're measuring. In terms of particles and plasma, Voyager is in interstellar space. The material around it comes from the galaxy, not the sun. In terms of gravity, Voyager is still in the solar system. It's still bound by the sun's pull, still following an orbit shaped by our star. This dual nature is part of what makes the boundary so interesting. It's not a single line. It's a series of overlapping transitions, each marking a different kind of change. And Voyager is showing us all of them. The sun's gravity will eventually let go. As Voyager moves farther and farther away, the sun's pull will weaken. At some point, the gravity from other stars and the general pull of the galaxy will become more important. But that transition happens over enormous distances, far beyond what Voyager can measure, far beyond what we can observe directly. For now, the spacecraft is still connected to the sun, still part of our solar system in the gravitational sense, still falling toward the sun, even as it moves away. That might seem contradictory. How can something be falling toward the sun while moving away? The answer is that Voyager is on an escape trajectory. It's moving fast enough that the sun's gravity can't pull it back, but the gravity is still there, slowing the spacecraft down, bending its path slightly. Over time, the sun's influence will fade. Voyager's speed will stabilize, and the spacecraft will drift freely through the galaxy, no longer meaningfully connected to our star. But that's millions of years in the future. For now, Voyager is still ours, still a child of the sun. Let's think about what the mission has meant for science. Before Voyager, our understanding of the heliosphere was based on theory and indirect observation. We knew the solar wind existed. We could measure it from Earth orbit. But we had no idea what happened at the distant boundary where it met the interstellar medium. Models were built, predictions were made, but they were guesses. Educated guesses, but guesses nonetheless. Voyager gave us ground truth. When the spacecraft crossed the termination shock, scientists learned the actual distance, the actual conditions, the actual behavior of the solar wind as it slowed down. Some predictions were confirmed, others were wrong. The real heliosheath was messier and more complex than models suggested. When Voyager crossed the heliopause, the same thing happened. Some expectations were met, others were overturned. The interstellar medium was not what everyone thought. This is how science works. You build models based on what you know. You make predictions. You test them against reality, and you revise your understanding based on what you find. Voyager has driven dozens of revisions. Its data has reshaped our picture of the heliosphere, our understanding of cosmic rays, our models of the interstellar medium. And the work isn't done. Scientists are still analyzing Voyager data, still finding new patterns, still updating their theories. This scientific legacy will last long after the spacecraft goes silent. The data already collected will be studied for decades. Future missions will use it as a baseline. Textbooks will reference it for generations. Voyager has become a foundation, a touchstone, a starting point for everything that comes after. There's also a technological legacy. When Voyager was built, the computers on board were state-of-the-art. They had 64 kilobytes of memory. They ran at speeds that modern smartphones would laugh at. But they were designed to be robust, reliable, capable of operating for years without maintenance. That design philosophy paid off. The computers have been running for nearly 50 years. They've survived radiation bombardment, extreme cold, and the inevitable wear of time. The engineers who built them made choices that prioritized durability over performance. Simple circuits, redundant systems, conservative designs. Those choices are why the mission is still going. Modern spacecraft are far more capable. They have better cameras, faster processors, more memory, but they're also more complex, more dependent on software, more vulnerable to failure. Voyager is a reminder that simplicity has value, that robust engineering can outlast flashy technology, that sometimes less is more. Future missions to interstellar space will need to learn from Voyager. They'll need to balance capability with reliability, performance with durability. The journey is long. The environment is harsh. There's no repair shop along the way. Whatever we send out there needs to be tough, needs to be simple, needs to be built to last. Voyager showed us what that looks like, and its example will guide engineers for years to come. The human side of the mission is just as important as the technical side. Behind Voyager are thousands of people, engineers who built the spacecraft, scientists who designed the experiments, operators who sent the commands, analysts who studied the data. Most of them are no longer working on the mission, Many are no longer alive. The Voyager program has spanned generations, but the work continues. New people have taken over from the old. Young engineers have learned from veterans. The knowledge has been passed down. This continuity is remarkable. It's hard to maintain a project over decades. People retire, priorities change, funding fluctuates, but the Voyager team has persisted. They've kept the spacecraft alive through budget cuts and policy shifts. They've trained new generations to carry on the work. That dedication is part of the mission story. The hardware is impressive, but the humans behind it are just as important. When you think about Voyager, think about them too. The people who have devoted their careers to this little spacecraft, who have spent years staring at data from the edge of the solar system, who have fought to keep the mission going when others wanted to shut it down. They're the reason we still have a connection to interstellar space. They're the reason the science continues, and they deserve recognition for that commitment. The mission also represents something about human cooperation. Voyager was built by NASA, an American space agency, but its discoveries belong to the world. Scientists from many countries have studied the data. International teams have published papers. The knowledge gained has enriched our collective understanding of the universe. The Golden Record was created with this global perspective in mind. It includes music and greetings from cultures around the world. It represents not just America, but humanity as a whole. In that sense, Voyager is not just an American mission. It's a human mission, a project that belongs to everyone who looks up at the stars and wonders. That spirit of shared exploration is one of the best things about space science. It transcends borders and politics. It reminds us that we're all citizens of the same small planet, floating together in the vastness of space. Voyager carries that message into the cosmos, and in doing so, it represents the best of what we can be. Let's return to the present moment. Right now, as you listen to this, Voyager 1 is continuing its journey. It's about 170 astronomical units from the Sun, roughly 15.8 billion miles from Earth. The spacecraft is moving at about 17 kilometers per second. That's about 38,000 miles per hour. Fast by human standards, slow by cosmic ones. Every year, Voyager adds about 3.5 astronomical units to its distance from the Sun. A tiny step in an endless journey. The signal it sends back takes about 22 hours to reach Earth. The power is down to less than half of what it was at launch. The instruments are operating on borrowed time. But for now, the data keeps coming. Scientists are still learning from it, still analyzing the measurements, still building better models of the heliosphere and the interstellar medium. This work will continue until the spacecraft falls silent. And, even after that, the data already collected will be studied for years. Voyager's scientific mission isn't over. It's just entering its final phase. There's something bittersweet about that, knowing that the end is coming, that within a few years, the signal will fade, and the last whisper from interstellar space will fall silent. But there's also something beautiful about it. The fact that we've had this window at all, this connection to a place so far away, this tiny thread linking Earth to the stars. Most of us will never leave this planet. We'll live our entire lives on one small world, under one familiar sky. But through Voyager, we've touched the cosmos. We've sent a piece of ourselves into the void. We've heard the hum of interstellar space. That's a gift, a privilege, something worth celebrating. And when the signal finally stops, we should remember what we learned, what we discovered, what we achieved. Because Voyager's legacy isn't just in the data, it's in the inspiration, the proof that we can reach beyond ourselves, the demonstration that human curiosity can carry us to places we never dreamed possible. That's the real treasure of the Voyager mission. Not just the science, though the science is extraordinary, but the spirit behind it, the willingness to explore, the courage to send something into the unknown. That spirit doesn't end when the spacecraft goes silent. It lives on in every scientist who studies the data, in every engineer who dreams of future missions, in every person who looks at the stars and wonders. Voyager showed us that the edge of the solar system is real, that interstellar space exists, that we can reach it. Now it's up to us to decide what comes next. The journey of Voyager began with a rare alignment of the planets. In the 1960s, scientists realized something remarkable was about to happen. Jupiter, Saturn, Uranus, and Neptune were going to line up in a way that only occurs once every 175 years. This alignment meant that a single spacecraft could visit all 4 giant planets using gravity assists. It could swing past Jupiter and use the planet's gravity to slingshot towards Saturn, then use Saturn to reach Uranus, then Uranus to reach Neptune. Without this alignment, visiting all 4 planets would require far more fuel, or separate missions taking decades longer. It was a once-in-a-lifetime opportunity, and NASA decided to take it. The original concept was called the Grand Tour. It envisioned 2 spacecraft, one visiting Jupiter, Saturn, and Pluto, and another visiting Jupiter, Uranus, and Neptune. But budget constraints scaled back the plan. The mission that emerged was more modest. 2 spacecraft, Voyager 1 and Voyager 2, would visit Jupiter and Saturn. If they survived, Voyager 2 might continue to Uranus and Neptune. As it turned out, both spacecraft performed flawlessly. Voyager 1 flew past Jupiter in March of 1979 and Saturn in November of 1980. Voyager 2 followed close behind, reaching Jupiter in July of 1979 and Saturn in August of 1981. And then Voyager 2 kept going. It reached Uranus in January of 1986 and Neptune in August of 1989. It remains the only spacecraft to have visited either of these ice giants. The images from these encounters were revelatory. Uranus, tilted on its side, surrounded by dark rings. Neptune, a vivid blue with the fastest winds in the solar system. Moons that no one had ever seen up close. Triton, Neptune's largest moon, turned out to be one of the most fascinating worlds in the solar system. It orbits backwards, suggesting it was captured from the outer solar system. Its surface is covered in nitrogen ice. Geysers shoot dark plumes into the thin atmosphere. These discoveries came from a spacecraft that wasn't even designed to go that far. Voyager 2's mission to the ice giants was an extension, a bonus, a lucky break. And after Neptune, both Voyagers kept going. They entered the Voyager interstellar mission in 1990. The new goal was simple: keep traveling, keep sending back data, keep exploring until the power runs out. That mission has now lasted longer than the planetary tour that came before it, and it has produced some of the most surprising discoveries of the entire program. The transition from planetary to interstellar exploration was gradual. For years, the spacecraft flew through relatively familiar territory, the outer heliosphere, the region where the solar wind still dominates. Then, in the 2000s, things started to change. The termination shock approached, the heliosheath loomed, and finally, the heliopause itself. Each of these boundaries marked a new phase of exploration. Each revealed something unexpected. And now, in interstellar space, the discoveries continue. The hum of the plasma, the density mystery, the magnetic field puzzle. Each finding adds to our understanding of this unexplored region. None of this was planned when Voyager launched. The interstellar mission was an afterthought. A what if that became a reality? That's one of the most remarkable things about the program. It has exceeded every expectation. It has outlived every prediction. It has achieved things that no one imagined possible in 1977. And it's still not done. Let's think about what it means to explore. Exploration is not just about going places. It's about discovering things, learning things, changing our understanding of the world. Voyager has done all of that. It went places. It made discoveries. It changed what we know. But exploration is also about the act itself, the decision to go, the willingness to venture into the unknown. That act has value beyond any specific discovery. It represents something about human nature, our curiosity, our ambition, our refusal to accept limits. Voyager embodies that spirit. It's a physical manifestation of our desire to know what's out there. And in that sense, the mission's greatest achievement isn't any particular finding. It's the fact that we did it at all. We built a machine. We sent it into space. We guided it past the planets. We watched it cross into interstellar space. We reached beyond ourselves. We touched the cosmos. That's exploration. That's what it means to be human. The data from Voyager tells a story. It's a story of the solar system's edge, of the boundary between our home and the wider galaxy, of the forces that shape our cosmic neighborhood. But it's also a story of human ingenuity, of decades of dedication, of the refusal to give up even when the odds seemed impossible. When Voyager stopped sending readable data in 2023, many thought the mission was over. The spacecraft was too old, too far away, too damaged to fix. But the team didn't give up. They worked the problem. They found a solution. They brought Voyager back. That persistence is part of the story too, the human element that makes the machine meaningful. Every signal from Voyager represents countless hours of work, programming, testing, troubleshooting, waiting. The data doesn't just appear. It's coaxed out of an aging spacecraft by people who care deeply about what it represents. Their dedication is woven into every measurement, every transmission, every discovery. And when we talk about Voyager's achievements, we should remember that the mission is not just a machine. It's a partnership between technology and humanity, between circuits and hearts. That partnership has lasted nearly 50 years, and it will continue until the very end. There's a question that comes up sometimes in discussions about space exploration. Why does it matter? Why should we care about a spacecraft billions of miles away? Why should we spend resources studying the edge of the solar system? Why does any of this matter to people here on Earth? There are practical answers. Voyager's data helps us understand cosmic rays, which affect satellites and astronauts. It tells us about the protective bubble that shields Earth from radiation. It provides information that could be crucial for future space missions. But there are also deeper answers. Exploration matters because it expands our horizons. It shows us that the universe is bigger and stranger and more wonderful than we imagined. It matters because it inspires. Children who see Voyager's discoveries grow up to become scientists and engineers. Dreams planted by distant spacecraft blossom into careers and innovations. It matters because it reminds us of our place in the cosmos. We are small creatures on a small planet in a vast universe. Voyager helps us understand that context, helps us see ourselves more clearly. And it matters because it represents the best of us, our curiosity, our creativity. Our ability to work together toward goals that benefit everyone. In a world often defined by conflict and division, Voyager is a reminder that we can do great things when we try, that we can reach beyond ourselves, that we can touch the stars. That's worth something. Even if you can't put a dollar value on it, the universe doesn't care about us. That's a hard truth. The cosmos is vast and cold and indifferent. Stars are born and die. Galaxies collide. Black holes devour light. None of it knows or cares that we exist. But we care. We look up at the sky and feel wonder. We ask questions about what's out there. We send machines into the void to find answers. That caring is remarkable. In a universe of mindless forces and indifferent processes, we are a spark of awareness. A brief moment of consciousness trying to understand itself. Voyager is an extension of that awareness, a sensor we've sent into the darkness to gather information, to learn, to know. The spacecraft doesn't think, it doesn't feel, but it represents something that does. It carries our questions into the cosmos, and every bit of data it sends back is an answer. A tiny piece of understanding carved from the vast unknown. That's the real value of exploration. Not just the facts we learn, but the act of learning itself. The effort to push back the darkness, to illuminate what was hidden. Voyager has been doing that for almost 50 years, and it will keep doing it until the last photon of signal reaches Earth. Let's consider the ending. Someday, probably within the next few years, Voyager 1 will fall silent. The power will drop below what's needed to run the transmitter. The spacecraft will stop sending signals. The line to Earth will go dead. When that happens, it won't be dramatic. There won't be an explosion or a crash. The spacecraft will simply go quiet. For the first time in nearly 50 years, there will be no signal from Voyager. The deep space network will keep listening for a while. Maybe they'll catch a faint echo, a last gasp. But eventually, they'll confirm what everyone knows. The mission is over. It will be a sad day. For the team that has worked on Voyager for decades. For the scientists who have studied its data. For everyone who has followed the mission and marveled at its achievements. But it will also be a day of celebration, a chance to look back at everything Voyager accomplished. All the discoveries, all the firsts, all the moments of wonder. The mission's ending doesn't erase its achievements. It just marks a transition from active exploration to historical legacy. After the signal stops, Voyager will keep moving, silently, endlessly, through the darkness between the stars. The spacecraft will still be out there, still carrying the golden record, still bearing witness to human dreams. It just won't be talking to us anymore. But the conversation we've had for nearly 50 years will continue in a different form. In the data archives, in the scientific papers, in the textbooks and documentaries and stories we tell. Voyager's voice will echo long after the signal fades. And maybe, in some distant future, someone will find the spacecraft drifting through space. They'll see the golden record. They'll decode its message. They'll learn about a small planet called Earth. A species called humanity. A civilization that once looked up at the stars and wondered. They'll hear our music, our greetings, our hopes, and they'll know that we were here, that we existed, that we reached out into the darkness. That's the final gift of the Voyager mission. Not just what it taught us, but what it carries forward. A message to the future, a record of our existence, long after everyone who built it is gone, long after the civilizations that launched it have faded. The golden record will still be out there, drifting, silent, patient, waiting to tell our story. The cosmos is filled with mysteries, dark matter that we can't see, dark energy pushing the universe apart, black holes where space and time break down. Voyager can't solve these mysteries. It's too small, too limited, too far from the places where the answers might be found. But it has solved some mysteries, smaller ones, closer to home. It showed us what Jupiter's storms look like up close. It revealed the violence of Io's volcanoes. It photographed the rings of Saturn in unprecedented detail. It mapped the termination shock. It crossed the heliopause. It measured the hum of interstellar space. Each of these was a mystery before Voyager arrived. Each is now understood a little better because of what the spacecraft found. That's how science works. One small answer at a time. One mystery solved, 100 more revealed. Voyager has given us decades of answers, and it has shown us how much more there is to learn. The universe is vast. Our knowledge is small, but every measurement helps. Every data point matters, and Voyager has given us more data points than anyone dreamed possible when it launched. That's its legacy. Not just the specific findings, but the foundation it laid, the baseline it established, the starting point for everything that comes next. Future missions will build on what Voyager learned. They'll start from a position of knowledge rather than ignorance. They'll know what to expect because Voyager went first. That's the nature of exploration. Each generation stands on the shoulders of those who came before. Each mission builds on what earlier missions discovered. Voyager was not the beginning. Pioneer came first. Mariner before that. A century of rocket science and radio communication before that. And Voyager is not the end. Other missions will follow, better, faster, more capable. But Voyager was the first to reach interstellar space, the first to cross the heliopause, the first to measure the hum of the cosmos. That firstness matters. It marks a turning point in human history. A moment when we stepped beyond the sun's embrace and touched the wider universe. Nothing can take that away, no matter what comes next. As we wind down this journey together, let's take a moment to simply sit with what we've learned. Somewhere out there right now, Voyager 1 is drifting through interstellar space. It's farther from Earth than any human creation has ever been. It's surrounded by the thin plasma of the interstellar medium. It's bathed in cosmic rays from across the galaxy, and it's still sending back data. The signal is faint, a whisper across 15 billion miles. But it's there. Scientists are listening, analyzing, learning. The hum continues. The measurements flow. The story unfolds. This is happening right now. As you listen to these words, as you go about your day, as the world spins and life continues. A small machine from 1977 is exploring the edge of everything we know. That's remarkable. That's beautiful. That's worth pausing to appreciate. In the rush of daily life, it's easy to forget that such things are happening. Easy to get caught up in immediate concerns and lose sight of the larger context. But the larger context is always there. The cosmos is always out there, and Voyager is always moving. Take a moment to think about that, to feel connected to something vast and ancient and ongoing. You are part of a species that sent a spacecraft to the stars. That's your heritage, your legacy, your story. Voyager carries a piece of all of us into the darkness, and in return, it sends back a piece of the universe. That exchange, that conversation between Earth and the cosmos, is one of the most beautiful things our species has ever done. And it's still happening, right now, as we speak. The sun is just another star from where Voyager floats. Think about that for a moment. The sun, which has dominated our sky and our lives for all of human history, is just a bright point of light from Voyager's perspective. The spacecraft is so far away that the sun's gravity is barely felt. Its warmth is a distant memory. Its light is just another speck among the millions of stars in the sky. From Voyager's viewpoint, we are small. Earth is invisible. The solar system is a tiny region of space shrinking in the rearview mirror. This perspective is humbling. It reminds us that our importance is local, that the universe doesn't revolve around us, that we are tiny creatures on a tiny world in an enormous cosmos. But it's also liberating. If the universe is vast and we are small, then our problems are small too. Our conflicts, our divisions, our fears, they shrink when viewed from interstellar space. What remains is wonder, the sheer improbability of our existence, the miracle that anything exists at all. Voyager helps us see that, helps us step outside our daily concerns and glimpse the bigger picture. That's one of the gifts of exploration. It provides perspective. It shows us our place in the grand scheme of things. And from that perspective, many things that seem important fade away. What remains is the simple fact of existence, the beauty of the cosmos, the privilege of being aware. Voyager is a messenger of that perspective, a reminder that there's more to reality than what we see from Earth, and that more is vast and strange and wonderful. The mission will end, but the journey continues. After Voyager falls silent, it will keep moving through space for millions of years, perhaps billions. It will drift past the sphere or cloud. It will leave the sun's gravitational influence. It will become a free-floating object in the galaxy. Other spacecraft will follow. Someday, perhaps centuries from now, faster missions will overtake Voyager. They'll pass it in the darkness and continue on to destinations we can barely imagine. But Voyager will still be there, still drifting, still carrying the golden record, a monument to what we were, a message to what we might become. The spacecraft doesn't know any of this. It has no awareness, no feelings, no understanding of what it represents. But we know, we understand, we can appreciate the significance, and that appreciation is part of the mission's meaning. The value we assign to it, the importance we see in it. Voyager is what we make of it, a scientific instrument, a historical artifact, a symbol of human aspiration. All of these are true, all of these matter, and all of these will endure long after the signal stops, because the mission isn't just about the spacecraft, it's about us, what we chose to do, what we chose to send, what we chose to say. The golden record speaks for all of humanity. It represents our best selves, our hopes and dreams and loves. That message will outlive any of us, will outlive our civilizations, will outlive perhaps our entire species. And in that endurance, there's a kind of immortality, a way of reaching beyond our brief lives and touching eternity. Voyager gives us that, a piece of ourselves that will last forever. That's worth everything. That's the real treasure of the mission, not the data, though the data is invaluable. Not the discoveries, though. The discoveries are remarkable. But the act itself, the reaching, the hoping, the sending of our voice into the void, that's what Voyager means. That's what it will always mean. A small machine, a golden record, a message of hope, drifting through the darkness, forever. There's something soothing about the scale of space. In our daily lives, we worry about deadlines and bills and relationships. We stress about things that seem urgent and important. But from the perspective of the cosmos, none of that matters. The universe continues regardless. Stars burn, galaxies spin, space stretches. And somewhere in all that vastness, a small spacecraft drifts through the interstellar medium, unhurried, unconcerned, just moving. That steadiness can be calming. It reminds us that not everything needs to be resolved immediately, that some things simply unfold over time, that patience is its own kind of wisdom. Voyager has been patient for nearly 50 years. It doesn't rush. It doesn't worry. It just moves forward, 1 kilometer at a time. There's a lesson in that, something we can carry with us through our busy lives. The universe has time, lots of time, more time than we can comprehend. And Voyager has become part of that timescale, a small piece of human creation moving through cosmic time. That's a peaceful thought, something to hold on to when the world feels chaotic. Our worries are temporary. Our lives are brief. But the universe endures, and Voyager endures with it. The night sky looks different now than it did before Voyager launched. Back in 1977, the outer planets were fuzzy dots in telescopes. The edge of the solar system was a mystery. Interstellar, space was pure theory. Now we have photographs, data, measurements. We know what those places look like because we've sent machines to see them. Voyager changed the sky. It transformed abstract concepts into concrete realities. And once you know something, you can't unknow it. Once you've seen the storms of Jupiter and the rings of Saturn, and the geysers of Triton, they're part of your understanding of the universe. That knowledge is permanent. It's woven into our collective consciousness. Every child who learns about the solar system today inherits Voyager's discoveries. Every textbook draws on what the spacecraft found. Every simulation and model builds on its data. Voyager didn't just explore. It educated. It informed. It expanded what humanity knows. That expansion is irreversible. The information is out there now, part of our species' understanding. And in that sense, Voyager's mission can never truly end. The data lives on. The knowledge persists. The discoveries endure. Even when the spacecraft falls silent, its voice will echo through every classroom and museum and documentary that shares what it found. That's a kind of immortality, a way of living on through what you've contributed. Voyager will have that, long after the last signal fades. The interstellar medium that Voyager is traveling through has been drifting for a very long time. The atoms floating around the spacecraft are ancient. Some were forged in the cores of stars that died before our sun was born. Some were scattered by supernovas millions of years ago. Some have been wandering through the galaxy since long before Earth existed. These atoms have seen things we can barely imagine: the birth of stars, the death of worlds, the slow evolution of the galaxy over billions of years. And now they're brushing past a tiny spacecraft from a young planet called Earth. It's a strange meeting, the ancient and the new, the cosmic and the human. Voyager is just passing through, a brief visitor in a region that has existed for eons. But the spacecraft carries something the interstellar medium has never encountered: a record of a conscious species, a message from beings who think and dream and wonder. That's new, that's different, that's something the cosmos has never seen before, at least not in this corner of the galaxy. Voyager introduces us to the universe. It says, here we are, we exist, we made this. Whether anyone will ever receive that introduction is unknown. But the gesture matters. The effort counts. We reached out. We tried. We hoped. And that hope is now traveling through space, moving past atoms that are older than our entire solar system, carrying our voice into the ancient darkness. There's poetry in that meeting, the young and the old, the brief and the eternal. Voyager bridges them, connects them, makes them part of the same story, our story, the story of a species that dared to explore. The final transmission from Voyager will be quiet. There won't be a dramatic last message, no profound final words, just data, like every other transmission, numbers and measurements and routine telemetry, and then silence. The deep space network will keep listening for a while, maybe days, maybe weeks, hoping for one more signal, but eventually they'll accept what has happened. The mission is over. The connection is broken. There will be press releases and retrospectives. Scientists will gather to remember and celebrate. The world will take a moment to acknowledge what was accomplished, and then life will move on, as it always does. But Voyager will still be out there, moving through the darkness, carrying the golden record. The spacecraft won't know that the mission has ended. It doesn't experience anything. It's just a machine, doing what machines do. But we'll know, and we'll remember, the decades of data, the countless discoveries, the images that changed how we see the solar system, the crossing of the termination shock, the entry into interstellar space, the hum of the cosmos. All of it will be part of our history, our legacy, our story of reaching for the stars. And the golden record will continue, drifting through the galaxy, waiting, perhaps forever, perhaps someday, for someone. We don't know what the future holds. We don't know if other civilizations exist. We don't know if anyone will ever find Voyager, but we know what we did. We know what we tried. We know what we sent into the darkness. And that's enough. That's the completion of a mission that lasted nearly 50 years. That's the end of a conversation with a machine we launched before most of us were born. That's the moment when we say goodbye to an old friend. Thank you, Voyager, for everything you showed us, for everything you taught us, for carrying our dreams into the cosmos. Safe travels. The silence that follows will be different from ordinary silence. It won't just be the absence of sound. It will be the absence of connection, the severing of a thread that has linked us to interstellar space for years. For the first time since Voyager crossed the heliopause, we won't have a direct line to the space between the stars. That silence will feel profound, not because the data was essential to our daily lives, but because it represented something, a presence, a witness, a piece of ourselves out there in the void. Without Voyager, interstellar space will return to being purely theoretical for most people. We'll still know it exists. We'll still have the data. But the living connection will be gone. That loss will be felt by the scientists who studied Voyager for decades, by the engineers who kept it alive against all odds, by everyone who followed the mission and cared about what it represented. But the loss will also be an invitation, a challenge, a question. What comes next? Will we send another mission to interstellar space? Will we build on what Voyager taught us? Will we continue the exploration that this remarkable spacecraft began? Those decisions lie ahead. For the next generation of dreamers and builders and explorers, Voyager showed us what's possible. It proved that we can reach beyond the sun's influence. It demonstrated that interstellar space is real and measurable and explorable. Now it's our turn to decide whether to follow. The cosmos is waiting. The questions remain. The darkness stretches. And somewhere out there, a small spacecraft drifts on. Silent now, but not forgotten. A piece of Earth. A message of hope. A golden record spinning through eternity. Good night, Voyager. Sleep well among the stars. We'll take it from here. As this journey through the Voyager story draws to a close, let's return one more time to the place where it all began. In 1977, the world was different. The Cold War defined global politics. Computers filled entire rooms. Communication meant telephones and letters. Against that backdrop, a group of engineers and scientists did something remarkable. They built 2 spacecraft capable of surviving the harsh environment of deep space. They programmed computers with less memory than a modern calculator. They designed antennas that could whisper across billions of miles. And they launched their creations into the unknown. No one knew if the spacecraft would work. No one knew if they would survive the radiation belts of Jupiter. No one knew if the computers would function for more than a few years. But they tried anyway. They built the best machines they could. They tested everything relentlessly. They prepared for every contingency they could imagine. And then they let go. They sent their creations into the void and hoped for the best. That act of faith was the beginning of everything that followed, the planetary encounters, the interstellar mission, the hum of the cosmos. All of it started with people who believed it was worth trying, who thought the questions were important enough to pursue, who refused to accept that some things were simply too hard. That spirit is still alive today, in every lab and observatory, in every classroom and backyard, in everyone who looks up at the stars and wonders. Voyager didn't just explore the solar system. It demonstrated what human beings can do when they work together toward a common goal. It showed that distance is not insurmountable, that time is not an absolute barrier, that even the most challenging problems can be solved with patience and creativity. Those lessons apply far beyond space exploration. They apply to every difficult challenge we face. Climate change, disease, poverty, conflict. If we can send a spacecraft to interstellar space, we can do anything. That's the real message of the Voyager mission. Not just what it found, but what it proved about human capability. We are capable of greatness. We just have to decide to pursue it. The Golden Record contains a message from President Jimmy Carter. It was recorded in 1977, just before the spacecraft launched. He spoke of hope, of unity, of the desire to connect with others beyond our world. He said the record was a present from a small, distant world, a token of our sounds, our science, our images, our music, our thoughts, and our feelings. He said we were attempting to survive our time, so that we might live into a future where we could join a community of galactic civilizations. Those words still resonate today. Nearly 50 years later, they capture something essential about why we explore. Not for resources, not for territory, not for practical advantage, but for connection, for understanding, for the hope that we are not alone. That hope drives exploration. It always has. From the first humans who crossed into new territories, to the sailors who crossed oceans, to the astronauts who walked on the moon. We explore because we hope. We hope for discovery, for understanding, for contact with something greater than ourselves. Voyager carries that hope into the cosmos. It embodies our desire to reach out, to touch the unknown, to say hello to whoever might be listening. Whether anyone ever hears that hello is beside the point. The important thing is that we said it, that we tried, that we refused to accept that silence was our only option. That's what makes Voyager beautiful. Not just the engineering or the science, though both are impressive. But the hope, the audacity of imagining that our small voices might echo among the stars. And now, as we reach the end of this journey together, let's take one last moment to appreciate what we've explored. We've talked about the hum of interstellar space, the faint, steady vibration of plasma that Voyager detected starting in 2017, the sound of the galaxy itself, humming in the background. We've talked about the density mystery, the unexpected increase in plasma density outside the heliosphere, the evidence that space is not as empty as we imagined. We've talked about the heliopause, the boundary where the sun's influence ends and the galaxy begins, the threshold that Voyager crossed in 2012, becoming the first human object in interstellar space. We've talked about the golden record, the time capsule of human culture, the message in a bottle cast into the cosmic ocean. We've talked about the people, the engineers and scientists who built and maintained the spacecraft, the dreamers who imagined what might be possible. And we've talked about the meaning, what it represents to send something so far, what it says about who we are. All of this is part of the Voyager story. All of it matters, and all of it will continue to matter long after the spacecraft falls silent. Because the story isn't really about Voyager. It's about us. It's about what we chose to do, what we chose to send, what we chose to hope for. The spacecraft is just a symbol, a physical manifestation of something much larger, the human desire to explore, to understand, to connect. That desire didn't begin with Voyager. It won't end when the mission is over. It's woven into who we are. Part of our fundamental nature. And as long as that desire exists, we'll keep reaching, keep wondering, keep sending our voices into the darkness. Voyager showed us what's possible. Now it's up to us to decide what comes next. The cosmos is waiting. Let's not keep it waiting too long. As you drift off tonight, perhaps to the sound of this voice guiding you towards sleep, remember that somewhere out there, Voyager continues its journey, moving through the darkness, carrying our hopes, listening to the hum of the universe. It's a peaceful thought, a comforting thought. We are not alone in the cosmos, at least not entirely. A piece of us is out there, traveling, exploring, representing everything we are, and that piece will keep going, long after we're gone, long after everyone we know is gone. It will carry our music and our greetings and our dreams. It will speak for us, forever. Sleep well. Dream of the stars. Voyager is watching over them for us.